So I forgot to turn on the microphone today for the lecture, so I'm going to give this lecture to an empty classroom. I was just saying today in class that it's been my dream to give a lecture to an empty classroom since I heard a story about a professor doing it 30 years ago. So I guess I get to realize my dream today. Okay, so we've been talking about uniform convergence, and the next result that we want to talk about has to do with why uniform convergence interacts well with integration. So we need to talk a little bit about integration. So let me give a quick introduction to Riemann integration. Okay, so you start off with a function on a closed and bounded interval, real valued function, and you assume that f is bounded. Okay, and we need a bunch of definitions. The first is that if you have a set of points, x0, x1, x2, that are contained all in the interval AB, we call it a partition if the first point is A and they are all increasing and the last point is B. Okay. So you have some interval AB and you have some x1, x2. You have some finite number of points, and they're increasing. The first is A, and the last is B. Okay. We introduce a little bit of a notation. So notation: let m sub I be the supremum of the values of f over the ith interval. Okay. So look at the ith interval. Right, look at the ith interval. You have some, let's say here's the fourth interval right here, right? And you take the greatest value, that value is called m sub I. Okay? We let little m sub I be the infimum over the same interval. And we let delta x sub I be the width of that interval, right? Okay. So this is delta x4 right here. Okay. And then we define something called the upper sum UPF, so the upper sum of f based on the partition P. That's defined to be the sum of the supremum of the values of f over the ith interval times the width of the ith interval over all intervals. Okay? So pictorially, in each interval, you find the supremum, you take that height, you multiply by the width of the interval, that gives you the area of a rectangle. Okay? And you do that for each of the intervals. Do that for each of the intervals. Take the supremum, and you get this value called the upper sum. It bounds the actual area under the function, if there is such a thing. Okay. And the lower sum is defined analogously, and the sum of the minima times the width. Right? So you get these rectangles that are below the graph. Right? And the sum of those guys is the area. And you see, of course, that the upper sum of UPF is always bigger than or equal to LPF. Okay, the upper sums and lower sums on P. Okay. Definition part 3. We define the upper and lower Riemann integrals of f on AB by taking the, so it's notated like this, integral with a bar over it of f dx. That's defined as the infimum of the upper sums over all partitions. Okay. So the way you want to think about this is, you have some partition, right? You have some partition, and you're taking the upper sum, right? The upper sum over that partition. Now, what happens if you take, if you refine that partition and you throw in some more points? Well, we're taking the we're going to take the supremum over each interval, right? So, but that interval is smaller than the original, right? This interval is smaller than the original interval, and so when we take the supremum, it's going to be less than or equal to the original supremum, right? Over here it's the same, but over here we actually get something smaller, right? And so you see what happens as you refine the partition, then the upper sum actually decreases, right? So here we've got this refinement. The supremum over here is like this, right? The supremum over here still stays the same. Okay, and so so you take the you look over all partitions, right? Even those that are getting pretty arbitrarily fine, and take the infimum of all upper sums, and that thing is called the upper Riemann integral. Okay, and you do the same thing for the lower Riemann integral is defined to be the supremum over all lower sums. Okay, and most important, if these two things happen to equal, then we say that f is Riemann integrable. F is Riemann integrable, and write this thing, the integral from a to b of f dx, for that value. Okay. So I think one way to get a good sense of this definition is to look at something that is not Riemann integrable. And so let's throw up a non-example. So let f of x be the characteristic function of the rational numbers. Okay, so it will give you a 1 if x is rational, but it will give you a 0 if x is not rational. Okay. And what you see is that if you look at this function, say on 0, 1, right, at every rational point, it takes on a value 1. At every irrational point, it takes on a value 0. Right? And so when you take the upper sums, if you take a partition, so take an arbitrary partition, and you look at the upper sums, well, the upper sum says, find the supremum of the function over that interval. Well, any interval is going to contain a rational points, so you know that the value is going to be 1 there, right? You multiply that by the width of the base, do the same thing on each of these guys here, and what you see is that the upper sum for this function, for whatever partition you take, is always going to be 1. Okay. And if you look at the lower sums, well, you take the minimum you take the infimum of the values over that interval. Well, again, you're always going to contain irrational points, And so you know that the minimum is always going to be 0. And then so you get the lower sum is 0. And so, right, if you're looking at the infimum of the upper sums, well, that's always going to be 1, right? The infimum of the upper sums is always going to be 1, and the supremum of the lower sums is always going to be 0. Right? So for this function, you see that the upper and lower Riemann sums don't agree, and so it's not integrable. Okay. Okay, I'm going to write down a bunch of properties, mainly to get to a fact that we're going to need when we talk about the uniform convergence and integrability. Okay, so the first thing is the following, so a bunch of observations. Okay. So start off with a function on AB, and suppose it's Riemann integrable, which implies that it is bounded. Okay, so we know that f lies between some small m and some big M. It's a bounded function. Okay. The first observation is that for any p, you have that the upper sum is bigger than or equal to the lower sum. Okay. Now we already knew that. Let's throw in a little bit more. That lower sum, you can also say that lower sum is bounded below by the lower bound of f times the width of the base, right? And that's obvious, right? Because if you look at this picture, say here is m, right? And you see that all the when you take the values, when you take the infimum of f, those are all bigger than or equal to m, and so all we're saying is that this thing here, right, this number that we get here, is going to be less than the number we get from the lower sum. Okay. So, and similarly, you have this sort of thing. Okay, so that's pretty simple. The second observation is that so let's start off with a definition. Say P and P star are both partitions of the same interval AB. And suppose that P star contains all the points of P. Okay, so you have one partition of AB, that's P. Let's say that it's these points here. Right? And then you have another partition that contains all the points of P, but also some other ones. Okay. If that happens, we say that P star is a refinement of P. A refinement of P. And like we said last time, like we said earlier, it's easy to see that if you take a refinement, then the lower sums are going to get bigger, right? Because you're taking an infimum over a smaller set, right? So the right, so the infimums are going to be higher. And similarly, right, if you take a supremum over a smaller set, then the value is going to become lower. Okay. Okay. And then the last thing I want to say is that if you have two partitions, P1 and P2 are partitions. You have two partitions, then we call the union P1 union P2 the common refinement. Of P1 and P2. Okay. So this is just the partition that contains all the points that are contained in P1 and P2. Okay. So it will be a refinement of P1, and it will also be a refinement of P2. And it is the smallest refinement of both of them. Okay. Okay, so now we can state the result that we're going to need when we talk about uniform convergence and integrability. So something simple, that if you have, if you look at the lower Riemann integral, then that's always smaller than or equal to the upper Riemann integral. Remember that this thing is the supremum of all the lower sums, and this thing is the infimum of all the upper sums. Okay. And here's one simple way to prove it. One simple way to see it. You say, well, suppose that the supremum of the lower sums is actually strictly bigger than the infimum of the upper sums, right? So one of them is strictly bigger than the other. Okay. Well, if that's the case, we can choose a partition P1 and choose another partition P2, so that the lower sum based on P1 is very close to the supremum here, and the upper sum based on P2 is close to the infimum here, right? So that one is strictly bigger than the other. So there exists P1, P2 such that L of P1 F is bigger than U of P2. Okay. And you can guess what will happen next. I'm going to take the common refinement, so let P star be the common refinement of those two. And you see that what will happen? Well, the lower sum of P star is bigger than or equal to the lower sum of P1, but that's bigger than the upper sum on P2, but that is bigger than the upper sum of P star. Right? As you refine it, the upper sum gets smaller. Right? But what would that say? That would say that there is a single partition where the lower sum is strictly bigger than the upper sum, right? But that's impossible. Right? The lower sum is always less than or equal to the upper sum. Okay, so you get a contradiction. Okay. Okay. So now let's go back to, that's the end of the quick introduction to integrability, Riemann integrability. Let's now get the theorem that about the interaction between uniform convergence and integrability. So suppose you have a bunch of functions that are all Riemann integrable, and I always abbreviate integrable like this. If Fn goes to F uniformly on AB, then f is itself Riemann integrable, and the limit of the integrals is actually the integral of the limit. Okay. So the integral of that limit turns out to be the limit of the integrals. Okay. And you remember that earlier we had some examples that showed that if you have pointwise convergence, then even if your functions are Riemann integrable, then the pointwise limit function might not be Riemann integrable. And we also saw that even if it is integrable, then you might not be able to commute the limit and the integral, right? We saw that there was there were examples where the limit of the integrals was 1, but the integral of the limit was 0, right? Okay. But what this says is that if we have uniform convergence, then it all works out like we would hope. Okay. Okay. So here's the proof. It's not that bad. We say, okay, let epsilon sub n be the supremum of the absolute value of fn x minus f of x over the entire interval. Okay. So you look at each function, right? You got this function f. You've got these other guys that converge uniformly to it, right? Right? And you look at the maximum distance between their values, like in this one, probably around here. Maximum distance between their values, and you call that epsilon sub n. Okay. Now, observe that the e sub n's, epsilon sub n's go to 0 since we're assuming uniform convergence. Right? Uniform convergence means that given a epsilon around f, given any epsilon tube around f, that we can pass some point, everybody lies inside the epsilon tube. Well, that's the same thing as saying that this epsilon f goes to 0. Okay. Okay. And then the second thing to observe is that f has to lie between fn plus epsilon sub n and fn minus epsilon sub n. Okay. Right. Okay. Okay. So now let's take the lower Riemann integral of the left-hand inequality and the upper right Riemann integral of the right-hand inequality. Okay. So taking this of the left-hand inequality and this of the right-hand inequality, what we get is that the lower integral of this guy is less than or equal to the lower integral of that guy. And we get that the upper integral of that guy is less than or equal to the upper integral of fn plus epsilon. And we always know that, we know from the theorem, that was the conclusion of our introduction to the Riemann integral, that this is less than or equal to that. Okay, now f sub n, we assumed we're all Riemann integrable, and when you subtract a constant off of it, then it's still going to be Riemann integrable. Right? You have a Riemann integrable function, you subtract a constant from it, it's still Riemann integrable. So both of these things, this is going to be equal to just the plain old Riemann integral of fn minus epsilon n, and this thing over here is just the plain old Riemann integral of fn plus epsilon n. so now what we observe is that we have this is less than or equal to this, which is less than or equal to this, which is less than or equal to this. Okay, so you've got four numbers, A, B, right? Four numbers, A, B, C, D, right? Ordered like this. And so the distance, if we look at C minus B, well, that's positive, but it's also smaller than B minus A. So let's write that out. C minus B, B is less than D minus A. Well, that's going to be just 2 epsilon, the integral of 2 epsilon n. But the integral of 2 epsilon n is just 2 epsilon n times b minus a. So you see what's happening, that the distance between the upper Riemann integral and the lower Riemann integral is bounded by some constant, like 2 times b minus a times epsilon n. Okay. Now let epsilon n go, let n go to infinity. Right? Then epsilon n goes to 0. And so what you see is that these two things have to be equal. Well, that tells you that f is Riemann integral. Okay. And further, what you see also is that we have that fn minus epsilon n is less than the Riemann integral of f. It's less than or equal to fn plus epsilon n. Right. If you let n go to infinity, and what you see is that the limit of the integrals of f sub n equals the integral of f. What you see is that the distance between fn and the integrals of fn and f is smaller than, again, 2 epsilon n times b minus a. Right, so in the limit, this thing converges to that thing. This number converges to that number. Okay, so that is the theorem about Riemann integrability and uniform convergence. Right, uniform convergence of Riemann integrable functions means that the limit is going to be Riemann integrable, and the integral of that limit is actually the limit of the integrals. Okay, now let's think about this in the case of infinite series. Okay, so suppose you have an infinite series. Suppose this infinite series, right, converges uniformly. Okay. In other words, that the sequence of partial sums k from 1 to n converges uniformly to this pointwise limit. Okay. Now, assuming that all these guys are Riemann integral functions on some interval AB. So what does this say? The theorem is going to say that then the series, the infinite series, is Riemann integrable. And two, that the limit of the integrals of the partial sums equals the integral of the limit. Okay. Now, rewriting this just a little bit, this is the integral of a finite sum here. So I can pull the integral out. Right. So, right, the limit of this finite sum is the integral of the series, right? Okay. Now I'm going to rewrite this thing as, right, because this is the limit of a partial sum, the sequence of partial sums for the infinite series, for this infinite series, right? So what we can say is this, that this is just knowing your definitions, that that you can change the order right? That if your series converges uniformly, then you can interchange integration. You can interchange integration and infinite summation. Okay, that's not true in general. That's not true in general. You can't. The infinite sum. A finite sum can always be pulled through the integral, but if it's an infinite sum, not necessarily. However, if it is a uniformly convergent infinite sum, then you can change the order. Okay. And this is called, people often call this term-by-term integration, right? You can, if you're integrating an infinite series here, then you can actually integrate each of the terms and then sum them. Okay. And you'll see this sort of thing when you're talking about power series in complex analysis. Right? You've got some power series, and it turns out you can just integrate each of the terms to figure out what the series converges to. Okay. So now the last thing we're going to talk about is the interaction between between uniform convergence and differentiability. So, okay, so let's get to it. Okay, so here it is. Uniform convergence and differentiation. Okay, so if you look at the example that we gave earlier, it actually shows that even if Fn converges to F uniformly, that does not guarantee that Fn prime converges to F prime, right? That the limit of the derivatives converges to the derivative of the limit. We do have a sort of a result in that direction. So, and this is sort of what you would hope, that in uniform convergence allows you to interchange differentiation and integration, just like uniform convergence allowed you to interchange integration and limit. So you're hoping that uniform convergence allows you to interchange differentiation and limit, but that doesn't happen. However, we do have something along those lines, which is the following. So suppose you have a bunch of differentiable functions, okay, and you know that the Fn, the derivatives converge uniformly. On the interval. And you know that there exists some point, x0, in the interval where where f prime, no, sorry, where the Fn converge. Okay. So you have uniform convergence of the derivatives, and you have a single point where the original functions themselves converge. Okay. In that case, you in fact can conclude that the Fn do converge uniformly. And that the limit of the derivatives is the derivative of the limit. And we didn't prove the whole thing in class, so I'm just going to prove the first part of this. So step one is that, in fact, we have that the Fn actually do converge uniformly to some f. Okay, so we want to show that using the Cauchy criterion, we want to show that given any epsilon, there exists an n such that if m and n exceeds n, then fnx minus fmx is smaller than epsilon on the whole interval. Okay. And what we do have is that the Fn prime converge uniformly. So that is, we can make the difference between the derivatives uniformly small on AB, right? And we know that we can make the difference between the Fn's as small as we want. Okay. So, right. So we'll use those two things together to show that Fn minus Fm must be as small. We can make that as small as we want. Right. 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 We'll make these guys the Fn at x0 close to each other. Right. And then we'll make the derivative of the difference tiny. Right. So the value will be small and the derivative will be tiny, and so the value on the whole interval will also be tiny. Okay. So so here we go. So 1 since fn x naught converges, there exists some point in time such that if we are past it, then fn x naught minus fn x naught is smaller than epsilon over 2. Okay. So part 2, since the fn prime converge uniformly, there exists an n2 by Cauchy criterion. There exists an n2 such that if we're past that point, then fm prime x minus fn prime x is smaller than epsilon over 2 times the difference between the width of the interval, right, for all x in AB. And you'll see why we have this, these 2's and the b minus a. Okay, so then let n be, as usual, the max of n1 and n2. If m and n are bigger than n, then both of these things happen. And what we see is that, right, the distance between fm and fn at x, well, that's the same thing as fm minus fn at x plus fm minus fn at x naught, sorry, minus plus the same thing back. Right, and we're throwing this thing in because this is where we have some controls. Right, we can make this thing as small as we want because the fn converge at this point. This is the point where we have convergence, right? And we throw in this thing, right? We've introduced this thing because we have control over the derivative, right? And so we're going to use the mean value theorem here. Okay. So then what does the mean value theorem say? The mean value theorem says that that there's going to be between x naught, between x and x naught, right? Between x and x naught, there's going to be there's going to be some point C where this holds true, right? And so, in particular, we have this, right? There's some point, we know that there's some point between x and x naught where this thing is bounded by the derivative of the difference evaluated at some point times x minus x naught. Okay, so this is equal to fn prime fn minus fm prime x naught times the distance between x and x naught plus this thing here, fn minus fn x naught. Okay. But remember, we're past the time when this thing is smaller than epsilon over 2 minus ba, 2 times b minus a. And this thing, x minus x naught, both x and x naught lie in BA, so this is smaller than the distance between B and A. And so what we get is this is less than epsilon over 2 times the distance between B and A. And this thing is smaller than epsilon over 2, and so we get epsilon. Okay. So we found a time past which Fn and Fn are close to each other in with respect at every point on the interval. So that is that the Fn converge uniformly to some function f. Okay, so next time we'll see that in fact the derivative of that f equals the limit of the derivatives of the f's and n's. Okay. Well. Okay, so that's it for today. Again,